Okay, hello everyone. My name is Joshua Bledsoe, and today I'm going to be giving you a quick look at polymer science. So, who am I? Well, very quickly, I was a student of Dr. Kopic's in 2015. He taught me Organic 1 and 2. And then, after having been at GGC for a while, I transferred to Georgia Tech, where I got my BS in chemistry. And then I went and worked in industry for a while at a company called Commence Medical, where I was working on superglue. And then after that, I decided that it was time to get my PhD, and so now I am at the University of Georgia, where I study polymer chemistry. So the idea behind this presentation is just I wanted to really quickly give you an idea behind, or concerning rather, what polymers are and why they're important. So essentially polymers are long macromolecular materials. They consist of many connected subunits called monomers. So I'm going to draw this out for you. If I approximate a small molecule as a dot here, or as a node, we can then connect all these dots together to form a long spaghetti-like chain. And then if we have a whole bunch of these in one big pot together, we're going to form this interconnected sort of spaghetti-like network of materials that are going to have some macromolecular properties to them. This is the fundamental basis behind polymers, and this is really sort of the central dogma that gives rise to all the different kinds of material and physical properties that you can get from these kinds of materials. So they constitute many of the most important modern materials around you today, whether that be PVC piping, which carries water to your house, or tires that you use to drive with, the cellulose acetate that your glasses are made of, or even something as strong as Kevlar, which is the primary component in bulletproof vests. Polymers are everywhere. There are two main classes of polymers, at least as how chemists classify them or organize them, but I'm going to focus on one of those today, and that is step growth polymers. Step growth polymers are specific in that they require two or more distinct reagents. These are the monomers, these little dots that I was drawing earlier. So we're going to have a dot, we'll call it A, and we have a different kind of dot, maybe I'll draw that as a square, and we'll call that B. And the important thing to note about A and B is that they are compatible with one another, but they are not compatible with self. So you cannot have an AA interaction, and you cannot have a BB interaction. The only kind of interaction you can have is an AB or a BA. So I want to quickly and just very briefly go through one of the concepts that builds into polyesters. So polyesters is one of, like I was saying, one of the foundational polymers. And the way that we get this A-B linkage is through a chemical reaction called esterification, or sometimes it might be called transesterification, depending on what reagents are used. Okay, so if we have this material here on the left, which I've designated as A, this has two alcohol groups on it. We're going to call this a diol, di meaning two, and all referring to the alcohol. And then this is a diacid, di of course being two again, and then acid referring to the carboxylic acid that's located on either side. So you might know from your experience in Dr. Kopic's class that an alcohol can react with a carboxylic acid. And so I'm going to write out that reaction mechanism here very briefly, and we're going to talk about that because this really has a lot of impacts on the polymerization. So I'm going to simplify this material for the sake of my drawing. So instead of showing this as a diol, I'm going to just chop this off. Okay, and I'm just going to act as if it's a singular alcohol, a regular alcohol. Okay, and then I'm also similarly going to do the same thing over here with this diacid. I'm just going to take this off for now, for the sake of simplicity, so I don't have to draw it a whole lot of times. Just make the drawing more simple. Okay, so if I start with my alcohol and I start with my acid here, and that's R prime. Okay, I can conduct my esterification in a bunch of different ways. Primarily, this is done through acid catalysis, but for the sake of drawing this, I'm just going to use H+ to show that this is happening in an acidic medium. Okay, so and this proton, by the way, is not going to be floating around by itself. I'm drawing it as if it is, but for the sake of your knowledge, it's important to note that this H+ is actually going to associate itself with this alcohol. In the actual pot of this material, the H+ is actually going to be on this alcohol, and that's where this transfer is going to come from. But for the sake of simplicity and brevity, I'm just going to have this H plus floating out in the air. And in fact, the first thing we're doing here is the electrons on this carbonyl oxygen are going to reach out and they're going to grab that hydrogen. And we're going to form this kind of molecule or this species here, where now we have a positive charge on this oxygen. Okay, and you already know with carbonyl chemistry, if you've learned any of that already, I believe you have, that you're going to have some significant charge difference between the carbonyl carbon and the carbonyl oxygen, and that's due to the polarity of that bond. And as a result, the carbon in the carbonyl is pretty electrophilic. Okay, so what we're going to have here is nucleophilic addition, or nucleophilic attack rather, at this carbonyl carbon, boom, right there. We're going to get resonance, and so this is the first sort of addition reaction that we're going to get, and we're going to form a tetrahedral intermediate. Okay, so with those electrons kicking up, we're going to form this non-charged species here, or at least with this region, and then we're going to have OH, and then R here, and then this is still R prime, OH. Okay, it's probably pretty obvious to you how this is happening right now, but if it's not, just rewind a little bit and see how I've gotten the oxygen reaching up and attacking the carbonyl here and pushing those electrons up. Oh, and let me not forget my plus sign here, okay? Because we have a charged species reacting with a neutral species, and so the resulting adduct should preserve those charges. Okay, this H is bonded to that O. The next thing we're going to have is we're going to have an intermolecular hydrogen transfer, or proton transfer rather. Okay, so we're going to have this oxygen will now reach out and grab that proton. Boom, it'll abstract it from this what was previously an alcohol, and we're going to form this product here, R prime OR, and now we have H2O. Boom. Now you'll notice that we have some productivity in that step because we have formed a very good leaving group in H2O. Okay, and so this is really the driving force behind this, is that since H2O is such a good leaving group, so stable on its own, the next step can actually liberate this water and give us our final products. Okay, so I'm going to show that here. The oxygen now can resonate back down. This bond can go over here to kick off water. So we're going to lose H2O here. And let's see, what are we going to be left with? We're going to have OH. We'll now go back to this kind of species where the positive charge is on the carbonyl oxygen. We're going to have OR, boom, R prime. And yeah, of course, our water has left the building, and so it's there. Now we can have another molecule of reagent can come and abstract this proton. And so I'm just going to, for the sake of simplicity, I'm going to subtract H plus here. This will disassociate because it will be grabbed by another molecule, and we'll be left with this material here. Okay, R prime O R. Okay, well, we've done it now. So we have formed an ester. This is called esterification because we're forming an ester linkage. So if you remember all of your functional groups, this is an alcohol, this is a carboxylic acid, and this is an ester. Okay, so you can see the ester linkage that we've made here, right? So that esterification is very important because now if I take this scheme that we've talked about here, I can then say, well, if my R right here has another OH sticking off of it, right? This OH was not used in the previous reaction that we just drew, but it still exists, that OH. And then on the other side of R prime, we have another one of these carboxylic acid groups, right? And we have much more of the diol and the diacid existing in the pot. Then we can very easily see another diol molecule could come over here and react with the carboxylic acid. Let me grab another color real quick so that I'm being more clear. Yeah, so like I was saying, another molecule of this could come and react here, and another molecule of the diacid can come over here and react with this now terminal alcohol. And so what you get here is this linkage where you have these procedural steps. That's why it's called step growth, right? A to B to A to B, and so on. Okay, and so this is really the formation of a polymer. And there's a lot more to be said about polymer science, but hopefully this has piqued your interest, hopefully just a little bit. If you have any questions or if you're interested, feel free to reach out to me or ask Dr. Kopic. I'm sure that he can help you with any questions you might have.